Okay, good. Well, good morning, everybody. We're glad you're here. Got just a tad of snow out there. Got here early enough you can actually eat your lunch, and we're especially glad for all those folks that came with money to give to Earhart. He's got a real smile on his face over here.
He hasn't checked his 401k today, does he?
No, don't do that. Don't do that. I thought the fourth quarter was bad enough. The first month is looking absolutely awful. So we've got a very interesting talk. It's from the perspective of, we keep hearing about these models that the IPCC uses and how they're predicting weather and all that kind of stuff, and how accurate it is out, 100 years or so. And what Mike and John Guslander are going to do is kind of go through what is all the science behind that. And I think you'll find it interesting. They actually test it on some other planets and things like that. But then we also just have to show you the variation of climate through time. People seem to think that the climate has always been what it is right now and has never changed. So we'll talk a little bit about that. But before we get to that, we'll grab a seat. I think there's a spare one over there or right here. Before we get to that, I thought
I have my cell phone in there, so
we've got some absolute dynamite field trips coming up. Ron Surdam is going to be leading a 4-day field trip starting July 21st. Can you just give us a quick discussion of what all we're going to see in here?
Sure, I'd be happy to. We're going to look at the Green River Formation, and it's the international standard for lacustrine deposits. We'll go from east to west, and go from the shoreline. We have crocodiles and so forth out into the middle of the lake, and we've got a lot of fossil fish. The strand line deposits are very interesting, things that are truly outstanding in terms of stromatolites, kind of strand line deposits you might expect. We'll also do a north-south traverse from the Uinta Mountains out into the basin. We'll see some of the tufa mounds that rival those that are out at Pyramid Lake, and we'll see a little bit of the mud flats full of saline minerals that go a little farther into the lake, maybe into the layered trona deposits. You'll see just about everything you might see in a lacustrine deposit, and it will be interesting to see what kind of interpretations you come up with.
Excellent. Sounds exciting and fun. Haven't quite. We'll have to see if we can negotiate with our chief cook to be along on that trip. The second major field trip we've got working is the first weekend in October. And John, if you could just say a quick word or two about that.
Yeah, very briefly. We are going to go out on that weekend and look at the Great Rift south of where most people go to Crater Center. So it's recent volcanics, and this is an area that one of the leaders, Shannon Govaniak from Idaho State, works with NASA out there. Actually, NASA uses it as a training ground for their astronauts. So it's very recent volcanics, all in the last couple of thousand years at most, right there. It's a very large rift system. So short of going to Hawaii, it's probably the best place in North America to see modern day basaltic type of volcanics, which is one of the two major types of So that'll be a camping trip. And again, where's Whiteman's not here? Hopefully.
I think we've got him lined up for that.
So it sounds like Steve's going to be contributing cooking-wise, which is always that should be a big draw as well. October should be a good time, temperature-wise, to be out there on the Snake River Plain. So that one will be a lot of fun, I think. You know, of course, it's not very far from here either, just like the Green River trip. There's a lot of neat geology within 3 hours of here, and that's good. So that one, I think they're both actually on the 2016 programming calendar. If not, they will be very shortly. I think they both are.
So the sign up for both of those, the summer and the fall one,
What we haven't
will come
worked out
up
logistics yet.
closer to
There'll be
the
an
time.
announcement.
Yeah, and those are not going to be, strictly limited. I mean, typically, if we have 30 folks, whatever, that's probably fine.
Is this one going to be a camping road trip also? Green River?
Camping road trip or hotel?
We really haven't decided that yet. We can do it either
It's
way.
kind of looking motel-ish,
Okay.
but we have to go down there and look at it.
Yeah, they're still working on that, so some more details on that one. And then, what was that dialogue between you and Rushford about getting lost in sand dunes?
Oh, there may be another field trip to the St. Anthony sand dunes, which are right over here. And the reason what John refers to is I went over there with Bob and a friend of his. He's got a four-wheel drive pickup. We drove out into the sand dunes. Turns out his four-wheel drive doesn't work. Two of it does. And so we were digging and other things. And finally there was a great big road grader that was about a quarter mile away. So I went running over, and he had a cable, and pulled Bob's vehicle out, and we straggled into Rexburg and had lunch. I covered. But so there may be, and those are very interesting. It's really interesting spot because the winds that come up the Snake River Plain, as they start to climb in elevation there, they drop the sand load, and those are very large sand dunes. One of Bob's students who works at Washington State has spent quite a bit of time studying those. So he's trying to line him up to give us a tour.
What time of year would that be?
It has to be when Bob is here, so it would be before late fall. For sure.
Probably August.
So, but we'll see on that. That one,
A little warm, but
Look, nice and warm.
nice and warm.
that one, the dates aren't locked down.
Yeah. Now, and then the last one I'll comment on before turning it over to Mike. Still enjoying his spectacular photography back here. And you have to name each of those places. That's Guslander, which is just up there. But anyway, the last field trip, you should have all gotten an email from me on the 15th about the field trip to Hawaii. It should be an extremely interesting field trip because Bob Tilling and Rick
Haslet.
thank you, John. I have actually set up not just them leading it as guiding the field trip, but as Bob put it, he says they pulled in almost all their chits as far as people that owe them in Hawaii to give us talks on all kinds of stuff, including the offshore drilling that has found a lot of what this thing really looks like, a volcano growing in the southern underwater. And then there's when we'll spend most of the time in Hilo. This is November 4th through 12th. Most of the time in Hilo.
It's typhoon season.
Well, and we'll even talk about the potential landslide, underwater landslide, on kind of the northeast coast of Hilo that could have serious impact on LA, which is kind of interesting little stuff. So all kinds of things. We'll also get up to the I think that one's available.
Yeah, I can look forward.
We'll also get up to the volcano house. We'll go to the top of Mauna Loa and with guides that can explain it all to us. Then we go over for a couple of days to Kona. The trip I think couples is $2,100 for each person as far as a couple, and I think it's $2,500 for singles without. And the airfare is in addition to that, and right now, there's actually some pretty good stuff. You can go, to get there, you pretty much have to go through Honolulu, from LA, Denver, different places. Coming back, interestingly enough, United actually has a direct flight from Kona to Denver. And so you can do it in two jumps, and it's about $1,100 for coach. So, and the key on all that is that on February 1st at 6 p.m. At 5:30, type me out a nice little note that you want to go on the trip, blah, 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 blah. And then wait till it gets really close to 6 p.m. and push the send button. And it's the first come, first serve as it comes in that way. And I would add, the good news is both of the guides have agreed that if we have 30 or 40 people want to sign up, they will run an additional trip in 2017. Haven't got them nailed down as to the dates yet, but so if we overflow one, there's luck on the others.
And the Grand Canyon sign-up was full in 6 minutes.
Yes, yeah, and in Scotland it took less than 10 minutes for the trip to be full. So don't be late on February 1st, the message. So, and without further ado, I'm going to turn it over to Mike, who's going to explain complex theoretical physics and hopefully not God knows what else. Come on in here, Harry. There's a seat right there. And that one back there.
pretty warm.
Too.
It's pretty warm.
Go back to the beginning. So maybe it would help to turn this thing on. Can you get to it? Okay, I'm going to park myself where I'm not in 2 minutes away.
And why don't you kind of close that door a little
All
bit?
right.
We'll try to keep it a little quieter.
Pull this one shut over here?
Well, almost shut.
Yeah,
They're still bringing in food, so.
Last one's coming.
Okay.
Okay, so this is going to be a talk on, as it's stated here, what drives the climate, and then we're going to take a look into the future, not deep future, but the future, and but look into the deep past to get a kind of a feel for what was been happening on Earth some time ago. So the outline is, I'm going to start out talking about the explanation of the greenhouse effect on Earth using some simple models. And then we're going to apply some of these simple models to the terrestrial planets with some success, actually. And then we're going to go into a lot of measurements of the climate, and many of them. And these mainly are, not totally, but mainly are coming from the IPCC 5 sets of digests. At the end of the talk, if you're interested, you can go up and see a few of them, but this is one of them, and there's 15 chapters. Okay, so it's a very comprehensive thing. The IPCC is the Intergovernmental Group on Climate Change and panel on climate change. And it started in about 1990, and every 7 years they give a new report. And so we are now on the 5th. So the 4th was in 2007, 2013 is the 5th report. And that's that set of, and that all is available online. Okay, so we're going to talk about some of the models that were used in that study, and those are called Earth system models. And we're going to compare the data with those Earth system models, but not just on average temperature. We're going to look at lots of things. Then I'm going to turn it over to John Guslander, my other partner in crime here, And he's going to take a look further forward. We're going to look at applying these same models out to 2100 and beyond. And then John's going to also take a look going back in time as well. All right, so that's the outline. So start off, the greenhouse effect. So the simple explanation is that the Earth absorbs visible and ultraviolet light from the sun. The Earth re-radiates some of the infrared light, now at a much lower temperature and frequency, up to the atmosphere. The atmosphere absorbs some of it, and then re-radiates some of it back. And this is kind of what's shown here in this cartoon. Sun, the Earth radiates up, atmosphere doesn't absorb all of it, but absorbs some of it, and then some of it is, and the simple way to look at the greenhouse effect is it's a blanket, but it's more complex than that. These are what are called black body curves, and every object above absolute zero will radiate radiation, and it all depends on the temperature. And this happens to be for the sun at 5280 K, sun surface. And this is the shape of it. Max Planck, over 100 years ago, worked out the math for those type of curves. But this measurement here, what this is actually showing though, the red is what's actually getting down to the surface of the Earth. So most of it is getting down to the surface of the Earth, but some of it is actually absorbed by the atmosphere above. Now this is the flip side of this. This is looking at black body at 14C. 14C happens to be the average temperature of the Earth. And so this is looking at the black body radiation at the top of the Earth's atmosphere. Now you look at the wavelengths here, you'll see a big difference. This is at 10 microns. 10 microns is 10,000 nanometers. So it's way off. So this is way off the size. So it's a very different frequency because the Earth is way cool. 14 is way cool. But 14C versus 14C versus 52K, 5280K. What you're looking at here is the actual radiation. This is the shape of the theoretical curve. Lots of them are missing, and they're missing in specific areas, so like water and CO2 absorb, and they're absorbing this, and so it's not actually getting out to the top of the atmosphere. Now this next I think view graph is kind of illustrative of what's going on. So I've just reproduced the plot that I showed earlier, just before, at the top of the atmosphere. And this is a different measurement. This is all measured data. This is measured at the surface of the Earth. And in particular, if you look at CO2 here, the peak in the CO2 reaching the surface of the Earth, it's at about 650, and this is in wave number, but you convert wave number to wavelength. It's right in there. It's right where that CO2 is theoretically should be absorbing, and it is, because none of it's there, but it's arriving at the surface of the Earth, re-radiated, back radiated from the cloud or from the atmosphere. And essentially, that's the greenhouse effect. It's this back radiation from the atmosphere is partially warming the Earth. Now, the net flow is up. I mean, the Earth is irradiating energy into the atmosphere and into outer space, but some of it is essentially getting reabsorbed. But the net flow is quite clear. It's out. It's not in. We're not actually taking a cold body and warming up. The net flow is out from the Earth. Okay, so this is also kind of interesting. I'm taking a little bit of John's thunder here, but I just thought I'd show this. In fact, I just got this information from John Heberger this week. It was from an earlier talk. This shows going back four ice ages, 4,000 years before, 400,000 years before present. And what you see here, this is the temperature, this is methane, and this is carbon dioxide. And it's just striking how well these align up with each other, and that every time there's a warming, there's lots of carbon dioxide. Now you could say, well, it doesn't actually prove what causes what, but in fact, as we believe very strongly, that the CO2 is responsible for a fair amount of this warming. And this is the same thing. This is all from ice core data going back 800,000 years from the present. And there's a little bit of that current present data this is what the CO2 level is about now. So it's actually higher than historical levels at the moment. Okay, so what we're going to do now is do a little math, but I'm going to keep it. John Guslander helped me out with this, and so we're trying to keep it more pictorial and less mathematics. But we're going to start with the sun, and we're going to start with something called the Stefan Boltzmann equation or law. And what that is, the Stefan Boltzmann Law is essentially the sum of all the radiation under that black body curve that I showed you just in the previous. And for mathematicians, it's the integral. It's the integral underneath those curves. And it's and it can be derived several ways, but that's one way it's derived. So it's exactly that integral. And it's a constant called the Boltzmann constant times the fourth power of the temperature of the object. So this is the total amount of energy that's radiated from a black body. Of course, the sun isn't black, but it's just the nomenclature. And that works out to a fairly large number at the sun's surface. Okay, so now let's approach the Earth. So now we're radiating ourselves out to the orbit of the Earth, and the sun radiation isn't as strong anymore because it essentially goes down by the ratio of the surface diameter of the sun to the radius or to the distance that Earth is away from the sun, and so it's down to 1368 watts per meter squared. So that's what's at the Earth's location. What the Earth absorbs is something else. Since it's only exposing one side of the Earth, the sun, at a given time, it actually works out to be the area. It's the shadow of the Earth against the flat plane. That's the surface that's actually being warmed by the sun. So you multiply, to get that, you multiply it by the area of that circle, which is pi r squared. And then, but the Earth radiates on the entire spherical area. And so you divide by the surface area, and you come up with 342 watts per meter squared. Okay, now the next several view graphs, don't bother reading what's over there. I'm going to explain it by just talking to it. But I included the words because if anyone wants to look at this stuff in the future, we're going to have it online. You can read the words, and it'll explain it for you. There's also footnotes on all of the references. Everything here is referenced. So you'll also be able to go back when you have that document and look up the specific references for this data. And for example, for this kind of calculation, this is pretty straightforward stuff, but the diagrams and all came from a certain place. So we'll start where we left off in the previous view graph. So we have the solar radiation at 342 watts per meter squared impacting. Well, two things happen. Now there's no atmosphere. We're going to take a case of no atmosphere, so ignore this layer here. It doesn't exist for this particular one. The Earth has an albedo of 0.306, and what that means is that's the amount of the sunlight that is reflected. So what's actually hitting the surface of the Earth is 1 minus that albedo, and when you do the math, it comes out to be 237 watts per meter squared. Now, one thing I didn't mention, and I showed that black, but maybe I'll just go back here. One thing I didn't mention when I showed this black body curve is that the radiation coming down from the sun is mostly in the visible and the UV, but it does go into the ultraviolet. But you can see the Earth's radiation is way in the infrared. It's way off to the side. But so this is most of what's in the radiation that's hitting the Earth. It's short. What's known in this parlance as shortwave radiation. And what I've done is, in these diagrams, is the shortwave radiation is shown in blue. Okay. So what happens is the Earth is absorbing 237 watts per meter squared. But we're in equilibrium, or I'm assuming we're in equilibrium. So for the temperature of the Earth to be at an equilibrium temperature, it's going to radiate that much energy back out from the surface, showing that other black body curve. And that's the same 237 watts per meter squared. And you see now I'm showing it in red because that radiation is at a very different frequency than the solar radiation. The solar radiation came in the visible and the ultraviolet, and the radiation from the Earth, because the Earth is way cooler than the sun, is totally in the infrared. And if you work the Stefan Boltzmann equation backwards and plug in the radiation, you come up with a temperature of 254 K or minus 18 C. So this is the temperature that the Earth would be if there was no atmosphere. And it would not be a habitable place. So the greenhouse effect is a good thing because we are here because of it. We would not be here if the Earth was not warmed by its atmosphere. Okay, so let's go to the next case where we put an atmosphere in it. And this is a very specialized atmosphere, not realistic, and I will make it a little more realistic in the next view graph. But I'm going to take the case of an atmosphere that's perfectly absorbing. It's going to absorb all of the radiation that's coming from the Earth, not letting any of it through. And then it's going to back radiate half of it back down to the Earth. So when you look at the absorption at the Earth's surface, you've got the solar radiation, which was in the shortwave, 237, and then the long wave radiation from the atmosphere, and you come up with 474. And if you do the reverse and use the Stefan Boltzmann law in reverse, that comes out to a temperature of 302 K or 29.5. Now that's an exaggerated temperature. That's essentially our body temperature. But that is the essence of the greenhouse effect. It is that back radiation is warming up the Earth. Now, there's been a lot of talk, and it's in the literature, that this violates the second law of thermodynamics because you're having a cooler area that's actually warming, in principle, the Earth, which is warmer. But that's not what the second law prohibits. What the second law says is that there's a net flow of energy, of power, from the hotter to the colder. Not that there can't be radiation from the colder being absorbed by the hotter. And you saw that first view graph where I showed the radiation from the atmosphere down at the surface of the Earth. And that's what we're talking about here, is that coming back down. And so when you do that, you get this 29C. And so all of the heat in this entire system, the Earth and the atmosphere, all came from the sun. And all that's happening is that the atmosphere is absorbing some of it and re-emitting it to the Earth. So basically what's happening is the Earth is losing heat because it's pushing up 474 and it's only getting back 237. It's losing heat, but it's losing less heat if the atmosphere wasn't there. And the same thing, it's the same argument, it's the same thing. You're a 30C, you come into a room like this, which may be at, it's 20C. It's cooler than you are, but you are just out at minus 20C. And why do you feel warm when you come into this room, even though the room is actually colder than your body? And the reason is that you're getting heat back, you're losing less heat than you would in outdoors. And so it's the same effect. The physics are different because in a room you have an atmosphere of convection, not radiation. But that would still apply even in a room if you had a room that was totally evacuated and it was all happening by radiation. It would still get warmer, but it would take longer. But that's the physics of it, and that's the physics of the greenhouse effect. We're not adding somehow cooling. We're not adding this cold stuff to the Earth per se, but we're just reducing the amount of energy that the Earth is losing. But it's losing. That's the bottom line. Okay, so the next one is the last one in this particular sequence. We're going to take a more realistic case where the atmosphere is not absorbing everything, and some of it's going straight through, and that's actually what happens. And I've taken the number of 0.77, so 77% is absorbed and 23% is going through. The reason I chose that number, or it's in the literature too, is that gives you a temperature for the Earth of 14C, 287 K, and that is the average surface temperature of the Earth. So this is a slightly more realistic model. It's still very specialized, and I'll show you in the next view graph what the actual story is. And this is the actual story. And I'll just, I think you can...
Can you go back to that one before?
Yeah.
So at this one, okay, you come out at 14C.
I come out at 14C because when this layer was absorbing everything and then re-radiating everything back, it came out to 29C.
Right.
And now we're only 77% of it is being absorbed and 23% is going through.
you arrived at the 77 by assuming 14, right?
Yeah, I worked it backwards. I mean, this is a simplified model. Well, it's in the literature too, but that's all I did. Was I said, okay, what do I have? What number do I have to make that to get to 14C? But you know, this is a very simplified model. This is actually what's going on, and I make the point.
Number of light bulbs.
A lot of light bulbs. Yeah, this is what's actually going on. Here's the sun up here, and so the first thing that's different immediately is that the sun is losing some of its energy, or some of its energy is being absorbed by the atmosphere before it gets to the surface. So only 167 watts per meter squared is being taken off the top, so to speak, of the deck, and only 168 versus 237 in the simple model is reaching the surface of the Earth. That's the first change. The second is because of the absorption in the atmosphere and the clouds, the back radiation is 324 instead of 148 in the simple model. The third difference is that the complete model, 104 watts per meter squared, is lost from the surface of the Earth through two additional effects that were not in the simple model. One is essentially thermals from volcanoes, and the other is evaporation. So that accounts for 104. Guess what happens when you add it all up? You come out with the radiation coming up from the surface, 388 watts per meter squared, versus what I did in the previous chart, 385. Now, is that a surprise? No, because the physics say the surface temperature is all related to the amount of energy or power that is being emitted. And so you get to 14C, the emitted radiation from the Earth has to be the same. And so this just shows more realistically where everything's coming and going. But you get to the same answer, which is 14C. Okay, so now we're going to say we've had some success with this simple model. Let's see if we can press our luck into the other planets, at least the other terrestrial planets. So the first line here is the temperature at the surface, assuming no atmosphere on the planet. And the second line is the actual measurement of the surface temperature. And you'll notice for Mercury and Mars, it's darn close. It actually agrees very closely. And so the simple model scores.
So that first line is the calculated temperature by the first model.
By the simple model, no atmosphere.
No atmosphere.
No atmosphere. Okay. Now we know, we just went through this in detail for the Earth. That doesn't work real well for the Earth because we have a significant atmosphere, whereas we know Mercury and Mars doesn't have much. But in fact, we were able to fix it, so to speak, with a single one-layer model. I mean, it's oversimplified, but it comes, so for 70, we come out with 288. In this case, he calls it 15. I was using 14. But the idea is with a simple one-layer. But let's look at Venus. Venus is a basket case because here we have a calculated temperature of 232, assuming no atmosphere. Well, everybody knows Venus has a hell of an atmosphere. And the actual surface temperature is 735. So even when I apply the one-layer model to Venus, I come out with a temperature of 260. And if I assume, and Venus, by the way, reflects most of the light from the sun. 80% of it is reflected off. Only 20% is absorbed. But even if I took it as 100% absorbed, I'm only getting to 390. So something is very wrong. Something very different on Venus, and we'll talk about that. Venus's atmosphere is very dense, and so it is an extremely bad assumption. You remember in the simple model, we assumed that virtually all of the radiation from the sun was getting through to the surface. And Venus, that's a very poor assumption. In fact, it's a better assumption to assume that none of it's getting to the surface, and it's all being absorbed at the top of the atmosphere. And so if we take the simple model with no atmosphere, and using the 132 watts per meter squared for the solar radiation coming down, you get a temperature for the top of the atmosphere of 210 K. It's probably going to be between that number and the 260 because this 260 assumes that there was some penetration of the sunlight through the atmosphere. The actual measurement from the Magellan satellite is 220 K. So it tells you that the assumption that the sun's radiation is not penetrating very far is absolutely correct. Okay. So then the question arises, well, how do you get to 730 K from the surface? And there's something called the runaway greenhouse effect, and we're going to talk about that real quickly. What that amounts to is that the sun is radiating the surface, and the surface has lots of water. The water is going to evaporate, and then the water is going to be in the atmosphere. Water is the strongest greenhouse gas, by the way, way stronger even than CO2. It's going to back radiate more radiation to the surface, which is going to cause it to increase. More evaporation is going to occur. This thing can go unstable. This thing can go what's called a runaway, where you get a positive feedback and the temperature is rising, rising, rising. And the reason it goes unstable is that there's a limit, there's a reference here for this, but there's a limit for a water-saturated atmosphere, how much radiation that it can be emit, and it's only 330. So if the demands of the surface are to, at a reasonable temperature, means that we have to lose more than 330, what's going to happen is the surface temperature is just going to rise very high. And what's going to happen is that's called a runaway effect, and this will continue until all the water is evaporated, and then it stops because the water's gone. This has almost certainly happened on Venus sometime in its past. And there's a huge clue about this. The hydrogen to deuterium ratio is 100 compared with 10,000 on the Earth. And this can be explained. Venus started out, and the thinking is, by the way, that Venus and Earth probably were very similar in terms of the amount of CO2 and the amount of water when the planets were when the solar system was created. But in Venus's case, it's lost all this water into the atmosphere, but because it has no magnetic field, the solar wind particles dissociate the water into hydrogen, deuterium, and oxygen. The heavier deuterium stays, the lighter hydrogen gets swept away by the solar pressure, solar wind, as well as just gravity. And what you're left with is a predominance of the heavy hydrogen, deuterium. And that's explained. So it really tells you, that ratio being such a difference, it really tells you that this thing had happened. And because of the fact that there's no water on Venus's surface, because there's no water, there's no plate tectonics. Water is critical to plate tectonics. There's no sequestration of the CO2, so all of it ends up in the atmosphere. 96% of the atmosphere in Venus is it's very dense, and it's almost all CO2.
And is the rest water then?
No, it's very little water. It's other things. I think maybe it's a trace of water,
So
but
these measurements are really small in that deuterium ratio.
Yeah. So there's very little water left.
Like a percent or a fraction.
Yeah.
Mike, you had a pressure for Venus atmosphere of almost 100 times that.
Yeah, we're going to get to that.
Oh, okay.
We're going to get to that right now. Okay, so the runaway greenhouse effect happened at one time, but it still doesn't explain why the temperature is 730 degrees now. And we're going to talk about that. So the runaway green, if you Google this and you ask, the answer is, it's the greenhouse effect. It's the runaway greenhouse effect. That's the answer in the literature, most of the literature. In fact, what the answer is very interesting. And the answer is that Venus's atmosphere, you notice there was very little radiation from the top. Venus's atmosphere is essentially a closed system, receiving very little heat in or out, and thus it's adiabatic. And the significance of that is an adiabatic atmosphere has a lapse rate of 7.8 K. And what is a lapse rate? It's a change in temperature with altitude. And this is the Magellan data, by the way. So you see, this is actually the temperature, and this is the altitude, and it's almost a perfectly straight line. It's almost a perfectly straight line. So if you take my simple case of 220 at the top of the atmosphere, by the way, the measurements show that the atmosphere is about 65 kilometers high. If you multiply 65 by 7.8 and add it to 220, you get to 727. So, voila. So basically, this also results in a very high surface pressure of 92 times the Earth. And so that's actually what is going on. Venus had this runaway effect. All the water is gone. CO2 is all in the atmosphere. None of it sequestered. This would have happened on the Earth without plate tectonics. So thank God for plate tectonics, because we'd be in the same boat. One of the other things, this is again more Magellan data. This is pressure. This is temperature, and this is pressure. And if you go to the very top of the atmosphere, which is right here, the actual temperature of what the green curve is Earth and the blue curve is Venus. If you go to the very top of the atmosphere, you find that the temperature of the two are almost identical, 220. So in spite of all the differences on the two planets, when you look at them from the outside, they're both absorbing and re-radiating the same amount of energy, resulting in the same temperature at the top of the atmosphere. So just an interesting anecdote.
Hey, Mike, you kind of blew by Mars. Are we going to come back to Mars?
Oh, because I didn't need to deal with Mars, because it was perfectly explained by the no atmosphere model. The temperatures were identical, virtually within a few degrees. So Mars and Mercury are simple cases, and the simple no atmosphere model works very well. And but you can see, in Earth, a one layer model does sort of well. But in Venus, it's not a one-layer model. It doesn't work at all. It's because it's a very different creature. And this is a little bit of a sidebar to this whole talk. And I just went through this calculation, so I had to show it to you. and I could probably publish this result.
I want to add one more thing to this.
Yeah, go ahead.
One way to look at Venus is actually much more similar to Jupiter and Saturn than it is to the other terrestrial planets. That's how you would be looking at temperature as you descended through the atmosphere on Jupiter, let's say. It would be a very similar procedure. It would get hotter and denser, and it would have almost nothing to do with the sun.
And Mike, just if I understand it correctly, Venus got in the shape it is because it basically burned up all of its water.
Right.
We now know that Mars had water. Why didn't the same thing happen on Mars?
Well, because okay, so maybe there was a runaway effect, but the key is what about the CO2? And Venus had a lot of CO2, and so the CO2 is not captured in this because of the lack of water. It's not in this certain. I don't know what the situation on Mars is. There isn't CO2 in the atmosphere to the same degree.
Okay.
But even close.
Mars is much smaller, so its gravity is much smaller. I don't know that that's exactly the reason, but that's definitely
that could easily. That's why it doesn't have any atmosphere at all.
Yeah, it
Because
can't hold on to
it doesn't hold on. Exactly. Yeah.
Don't overlook the importance of the magnetic field.
Oh, yeah.
Because you got Venus and Mars, neither of them have magnetic fields. And the atmosphere can be swept away or dissociated.
Yeah.
On Mars, the oxygen, I think, is in the soil, in the
Yeah,
rocks.
okay.
And in Venus, apparently they had a lot of carbon, so now it's in the carbon dioxide.
Yeah. But that's right. The lack of a magnetic field on Venus was very important to this discussion. By the way, I mentioned it, but I kind of talk about a lot of things pretty fast.
We've noticed.
Do you calculate the lapse rate, or is that
You calculate it.
Okay.
You calculate it. It's actually a number. It relates to the specific heats and of the gases, and you take the specific heats of CO2, constant volume, constant pressure, and you can calculate that lapse rate. Yeah, and it comes right out. And so that
So you
calculate.
derive that number.
I derived that number and then applied it.
No, it worked beautifully.
Yeah, it works.
This
is not well known. This is not well known.
There's an independent way to get the temperature too, and that's to use an equation of state, like van der Waals equation of state, and just plug in the atmospheric pressure and density, which can be measured by the probes, and calculate the temperature, and you get roughly that temperature in water here.
Okay, so enough of a little bit of a diversion on the planets, but I thought it was interesting for several reasons. One is it just shows you the application of the simple models are not totally useless. They actually give you some insight. And that's why I wanted to show you these, because it gives you some insight as to what's going on even in the more complex cases. Because the more complex models have all of this in it also, but they just they include a lot more effects. So we're now going to switch gears, and we're now going to look at data, not measurements for a while. And we're going to talk about measurements. So the question is, how do we know that the climate is warming? And this diagram comes out of one of the IPCC Chapter 7. And we know it for several reasons. One is ocean heat content is going up, sea surface temperature is going up, marine air temperature is going up, sea ice is going down, water vapor is being evaporated, air temperature is going up, glacial volume is going down, snow cover is going down, and temperature over land is going up. Okay, here's the data. I'll walk you through this fairly slowly. The first is, this is data from 4 different data sets. It appears in the IPCC. They just do a nice job of collecting it, but this was data measured in 4 different ways. But so the first is the temperature, and this goes back from 1850 to 2010, right here. And so this is the temperature of on the Earth, average land temperature, air temperature, which means very close to the surface. And you see the increase that's occurring in the last 30 years or so. Sea surface temperature also rising. This is marine air temperature also rising. This is sea level. 6 data sets of data, by the way, involved in these curves, also rising.
What's your scale on that one?
This is millimeters. 50 millimeters. So the sea level has changed from -150. This goes back to essentially pre-industrial revolution up to about 80. So it's changed about 230 millimeters, almost a quarter of a meter in that time period. This is the summer ice extent in the Arctic, and this is in an area, surface area, a kilometer squared. And it's going down really dramatically. Then you go to these smaller ones. This is now just between 1940 and 2010. This is the atmosphere, tropospheric atmosphere, and it's increasing. Ocean heat content, 5 data sets, no question it's going up. What's that? Units. Yeah, it's joules. Yeah. Times 10 to the 22nd, yeah, anyway, it's a scale factor here, but yeah, it's joules. And this is humidity, this is northern hemisphere snow cover going down, and this is glacier ice balance going down. 3 data sets, so there's a fair amount of good data. And so, and I don't show it here, but the land storage water hasn't changed very much.
Hey,
Is there a comparable one for the Antarctic?
Oh, yeah, there is. We'll see that shortly. I'll come back to that. But the reason I'm showing the Arctic is it's way dramatic in the Arctic. The Antarctic isn't losing. Actually, the Antarctic is gaining ice. It's not losing. There's a small area of it in the Weddell Sea, you'll see later. It's losing, but by and large, it's gaining.
Is there a quick and easy explanation? If I look at the temperatures, not the surface temperature, but sea temperature and some of these, they all start kind of kicking up about 1900.
Yeah.
Yet on the bottom curve, the extent of the ice, everything's kind of happy until we get to about 1950 something. And then we start dropping it off. So there's this huge delay or lag.
Yeah, you'll see. Yeah. You'll see that the temperature on the Earth isn't really starting to kick up until about the same time as this. But you're right, this is kicking up. These numbers are kicking up. So the question, that's a good question.
But it takes time for the heat to move into the ocean, the deep ocean.
Yeah, but this is going backwards in time. So it says that somehow something is happening in the ocean way earlier than the heating in the atmosphere.
Oh, I see what you're saying.
Yeah, so I don't have a good explanation for that. It's an interesting observation.
Sea's not rising, the land is sinking.
But the bottom line is it's all going up, okay, except for the ice is going down and snow is going down. The next is that it's not going down uniformly, and I found this kind of interesting, and when we talked about the Arctic ice, I kind of hinted at it. This is the northern latitudes, the same thing, temperature anomaly versus time. And you can see that, well, there's 2 things that are interesting. There was a cooling that went on in this time period, but then it really starts rising. And if you look at the low latitudes, that is 23, around the equator, you see a steady rise, but much less dramatic than this. And then in the southern latitudes, sort of the same thing. It's much more gradual rise. So there's something called polar amplification working here. We just happen to live in the side of the top of the Earth here, where the effects of global warming are amplified. And there's a number of reasons for that, because there's a feedback effect. Once you start losing snow and ice, the albedo goes down and more of the sun is absorbed. And that's probably the biggest effect. But there's ocean circulation, there's anthropogenic soot in the Arctic environment, in other words, soot from carbon soot on the surface, and increases in cloud covering water vapor. This is data that NASA has released showing the temperature trends between 2000 and 2009, recent stuff, but you can see how much in the northern hemisphere, the red indicates, the red, far red here is 2 degrees C. So the temperature increase in the northern hemisphere is way higher than it is elsewhere. So this is, even though it's interesting to look at the global averages, there's detail buried underneath that. And this is again all data. This is not no calculations here. This looks at the rate of change of temperature. So we're talking about degrees C per decade. And here's the color chart. This is looking at from 1911 to 1940, and you can see there was some warming, particularly up. The rate of change was high, and mainly in the northern hemisphere. Big change between 50 and 80, but then in the last 30 years, big change, lots of increasing temperatures per decade in the northern hemisphere. And okay, and now let's talk about ice and snow and such. So the top chart here shows glaciers. This is the cumulative loss in gigatons of ice. And so you see this. This is glacier. This is land, land-based glacier. Then these are the ice sheets. The green here is Greenland, and Antarctica is the blue. And so there has been a loss, or a cumulative loss, of ice on the ice sheets of Greenland and Antarctica. It's focusing on Greenland. Yeah, but look, there's a number here. It's very interesting. In Greenland, the ice loss went from 34 gigatons per year in the decade from 1992 to 2001. It's up to 215 gigatons per year in the last 10 years. Huge change. And you can see this. This is a kind of a polar plot. This is the change of an ice in Greenland between 2003 and 2012. And these numbers, this is centimeters per year of equivalent water loss. And it's down -10 here, -2 in this region, mainly in the southern and the western area. But if you look this between 2003 and 2006, it's not nearly as dramatic in that period. What it is the last 6 years, we're down to -16 in this area. So this has really jumped up in its effect, big time. And this is Antarctica. So here you see some blue. I mean, blue means gain. And so this is, this again is ice gain. And then the one area of loss is right here in the Weddell Sea.
That's not the Weddell Sea.
What?
That's not the Weddell Sea, I don't believe, Mike.
I think it is.
The Antarctic Peninsula, if you go at about 11 o'clock.
Okay, yeah, that's it.
Yep, the Weddell Sea is to the right of that.
That right there.
No. If you go up at 11 o'clock, you just follow that straight up.
I don't think so.
I've
But,
been there,
okay.
Mike.
You've
It's
been
the
there.
Weddell
Okay.
Sea.
All right. Yeah. Anyway, this area, whatever it is
The red area.
The red area, but it's confined. It's confined. Is, I guess, the point.
Any good explanation?
Yeah, why?
Well, yeah. Well, of course, you have a continent here. That's John. You have a thought, John Guslander. You were.
It's complicated from what I read, that it depends on how those ice sheets are grounded on the sea floor and the currents. I mean, the biggest difference is between Greenland and Antarctica is ocean currents. You have to keep that in mind. Like Greenland is almost directly connected to the tropics because of the Gulf Stream, where Antarctica is surrounded by the circumpolar current, which isolates it. But why there's that one little difference here, I don't know.
Yeah, and you'll see later when we start talking about the modeling. The model predicts this, by the way. So
I thought it was precipitation actually has increased in
Antarctica as well,
which could be due to more water vapor. And
Well, isn't there a tremendous difference in the land surface area? in the north hemisphere versus the south hemisphere,
Yeah, there is. It's much more overall.
which would change the radiation problem
Yeah, much more
and
north.
complicate everything.
Mike West has a comment.
Yeah, I know.
Oh.
It seems to me that I've read that area that's red has a large ice shelf that is being undercut by the currents, and that's why it's melting as rapidly. It's actually the ocean water. It's rising temperatures of the ocean.
The next chart is just something else that's interesting too. This is the terminus, glacier terminus shrinkage. And the units are hard to see, but that's 2 kilometers, 2,000 meters. And this is Alaska, Western United States. And they're all going down. But what's interesting, to the point that John Walat made earlier, this all started way before. I mean, this has been going on for a long time. The scale here, this starts in, I think, in 1850, and so this has been going on for a while, even before the dramatic change in temperatures that we're now seeing. There are some really dramatic effects, like over here in Scandinavia. Some of these things can happen extremely fast, but anyway, this is kind of close to our heart too. You're looking at Western United States and the West. I thought I showed this chart. So now we're going to, so that's some data, and I'm going to talk about the models. And as I mentioned, the IPCC is in its 5th generation of reports and models. And simplistically, it started in 1990 with very simple, crude models, and they've gotten more sophisticated. This shows the density of the grid has gotten higher, but there's a lot more to it than just the density of the grid. For example, you know how I showed the Earth had the simple 1-layer model? Well, these models have as many as 80 vertical layers in them. So, and on top of that, the 4th generation made some big changes. They included atmospheric effects of convection, clouds, aerosol. They included ocean effects associated with turbulence and density, gravity, force currents. They included land effects of vegetation and soil. They included sea ice effects of different albedos for different types of ice, melting, bare ice, snow-covered ice, open water. The 5th generation models took all of this, but then they've added some additional things. They've added physical, chemical, and biological, biochemical processes. For example, one of the big changes is they've included the carbon cycle. So we now they're modeling the sinking of carbon dioxide and methane in the oceans. Ocean acidification has been included. Aerosol particles with a feedback effect with the atmosphere and the radiative transfer. Land use changes such as deforestation and wildfires, the ozone hole and recovery of the southern hemisphere climate, and also time-varying stratospheric ozone concentrations in chemistry. So a lot more chemistry has been included in the 5th generation models. So this is the first of the comparison charts, and it's the first one everybody uses. It's the actual average surface temperature as a function of time from 1850 or so all the way up to 2010. Now this is a messy looking graph, but let me explain it to you. The black is the data, and it's probably, I think I showed you on the previous, there's probably 5 data sets in there. So the black is the data. The individual models, and there's probably about 50 of them in here, are all this spaghetti. And the individual models are different from each other. But there is something called the CHIMP model, and the CHIMP is the Coupled Model Intercomparison Project. And that is an average of all these models, and that's the red line. And you'll see how the red line does. I mean, it's following these dips. I mean, it's following the shape of the black line very closely. Maybe, but not quite perfectly in the last 10 years. And we see that the red line is going up, whereas the data seems to have almost flattened out. And if you look at the actual, this is a plot of the various distribution of models in terms of degrees C per decade. And this is in the last 14 years. This is the data here, and this is what the distribution of models are. So most of the models are overstating the warming effect. But if you go to the previous 15 years, most of the models are understating the overall effect. And if you go for the whole period of 60 years, the models are actually doing pretty well over that entire period. But there's a somewhat of an anomaly in these two periods, overstating and understating. And there's been some speculation, if you read the details in the reports and you go and say, why is this happening? There's some speculation. There's a few models that got it right. And they apparently took the strong El Nino effect that occurred in 1998 and into account more into account than the other bulk of the models did, and they came closer. But there seems to be another explanation, which this is a recent paper I just got out of the American Institute of Physics, and this is this temperature plot over only from 1980 on, and different data sets. Then if you the color here is the model, and I'll show you what the model. What's interesting about this paper is that it shows you the El Nino southern oscillation effects separately. It shows you the volcanic aerosol effects here, and it shows you the anthropogenic effects, this is man-made, pretty much continuing to rise. But one thing that this recent paper is showing, that the solar radiation is taking a dip in this period. And so when you add all this together, you get this. It's very similar to what the data is showing. So this is something that most of those other models I just showed you that were completed in 2013 did not show. So take this for what it's worth.
Yeah.
But, yeah.
What the solar radiation? So they've got that converted to the temperature impact at the surface of the Earth.
Yeah.
Okay.
Well, they show the change in solar radiation here, and what the unit here is another question. But when they combine these, it has the effect of rolling this model.
Well,
Do they take the solar radiation measurements at the time when you have those huge eruptions on the sun? Because those things would have a dramatic effect on the radiation.
Well, you
on
see,
the Earth.
there's the 11-year pattern here.
I don't know what that means.
Well,
That's
it's
the
the sunspot cycle.
Yeah.
The sun radiation does vary with 11-year pattern.
Well, you actually have variations
Oh, yeah,
much stronger in smaller periods
Yeah, well,
of time, because
Well,
if
you can see the data bumps here too.
but if you take a look at the Stefan Boltzmann equation and take a look at what is happening in a short length of time, you will see radiation changes to the Earth as much as 30%, depending upon how large it is. And you don't see that on there. You don't see the frequency. You don't see where it's happening on the Earth, because you're really not measuring it on a continuous basis.
Yeah.
And so all of this is really good work, but we really don't know what's happening. And just because we see very different radiation from the sun on short times, that may very well be the reason we're seeing such screwball climate changes. And we're not taking any of that into effect. And I don't understand, and I'm not sure I know just how the Magellan measurements are made. Are they made continuously, or are they made?
Well, the Magellan is, of course, gone. I mean, it was a satellite on Venus.
Well, so we don't have any measurement now at all.
No, not from that one.
So,
anyway.
you know, if we were to have a satellite which would actually do instantaneous measurements, we'd be able to take a look at both the Earth radiating out, which is part of your equation, as well as the radiation from the sun, which is really substantial.
Yeah.
And I think we're spending, hundreds of billions of dollars on stuff that we really don't have good measurements.
The other factor, though, to take into account is the slowness of some of these processes. You don't.
Yeah. Oh, yeah.
Yeah, you just jump up.
Well,
the ocean is going to respond real slowly.
Well, that's why I asked about the land surface
Yeah.
versus the ocean,
Yeah.
because there's a really a large delay
Yeah.
on it. And the other question I have is, we take a look at average temperatures. Would we have the same effect if we took the mean temperature? because in the average, when you take averages, large discrepancies would change the average substantial, whereas in a mean it would not.
Yeah.
And so somehow we need to get back to some fundamentals in doing climate change.
I'm sure there are several satellites up there that are constantly monitoring the sun. I'm sure they know what what's
Well,
coming
the
from
only
sun.
part about that is I've tried, and I'm not very good at into the internet. The only thing I found on the internet was when they were having the measurements, they wanted to save them, so when there were sunspots and eruptions on the sun, they turned the measurements off because they didn't want to damage the equipment.
But there is satellites that, we have some curves we didn't put in here, but they measure the entire black body frequency continuously. I can't remember what it's called, SONUS. I can't remember, but you can get the spectrum of the sun at the top of the atmosphere, and then they're also flying airplanes at different altitudes, so you can get the spectrum at the different slices, and then you get the spectrum at the surface looking up, so you can see what's reflected down. And so there are many continuous measurements right now.
Yeah, okay, so.
We just didn't put that in.
So John, do you know on that solar radiation curve, is that a surface measurement or is that at the top of the atmosphere? And
That would be at the top of the atmosphere and the output of the sun before it's interacting.
Okay,
with
good.
it.
Good, because if it's at the surface, then you've got all the atmosphere
Big
involved.
chunks of
Yeah,
pulled
yeah,
out of it.
okay, good.
Okay, so more data, now this is measurement and data and comparison. We just talked about the average global temperatures. This is now actually predicting, these models do a lot more than that. They actually predict what the surface temperature is all around the globe. And so the top one on the left is a average of the mean surface temperature between 1980 and 2005. And it's calculated by as the mean of all of these ESM models, and so you can see it. So this is not warming. This is the actual average surface temperature as calculated. This is the multi-model mean of the precipitation in the world over the same period. The lower plots are errors. So this is the multi-model absolute error comparing this to the actual measurements. And most of this is yellow, and yellow is in the 1 degree, but there are certain areas where the errors are bigger. In the tropic, in the Arctic, in Antarctic, and in the Himalaya, and some other areas, you're getting bigger areas. But overall, it's a pretty amazing, I think, from a theorization standpoint, pretty amazing job of actually calculating what the temperature distribution is across the world, and over here on precipitation. And again, it's making small errors mostly everywhere, but some larger errors in the tropics. And but it's I personally think that it's an amazing result. The next is something called cloud radiative effect. This is some of the most complex stuff in these models because clouds change everything. So over here on this left side is the shortwave cloud radiative effect, global mean. And this is measured data, and I forgot over what period, but I just show it for illustrative purposes. The color this is in watts per meter squared, and the color, the deep blue means it's way down here in 50, and the global mean of the shortwave cloud radiative effect, this is the amount of sun radiation that's not getting through, is minus 47.3 watts per meter squared. So that's a big number. And this is the long wave radiation, and what is that? That's the radiation coming up from the surface. And it's going to be warming. The clouds are having a warming effect, so it's all red. And this is the combined here. So this is data. This is now a combination of data and calculation. And what this is the zonal, is the cloud radiative effect. This is the short wave up here, long wave here in total. So in the short wave case, here we have the poles. So it's minus 90 degrees, minus 60, equator, plus 90, and Arctic. And so the solid curves are the data. The solid dark curves, black curves, are the data. And the red curve is the chimp mean. Pretty bloody amazing. It does an extremely good job of doing this, as well as, and you'll notice that all this, the sign, these are all negative because you're blocking radiation from the sun. These are all positive because you're essentially blocking the surface, the temperature loss from the surface. And and again, the calculation and measurement is remarkably close. And this is the composite of the whole thing. So, just another example of trying to show two things. One is that what the models include. They include this stuff, and how well the models are doing in actually calculating this with experiment. So now we turn to the sea, and there's I'll walk you through these. We'll spend some time on this first one here. The sea here this is observed and modeled sea level, and these are in millimeters. So this is 0, 50, 100, from 1900 to 2010. The colored lines are all data, different data sets. And the solid black line here is the model average, only including thermal effects. And this I found, a lot of you probably knew this, but most of the sea level rise is not due to ice melt at the moment. Most of it is due to the fact that the sea is warming, and as it warms, it expands, and that's caused the rise. So this black line is just including the warming effect of the ocean, and if you look at the 0 here, see that a good chunk, most of it that's all warming, from the warming effect, the expansion of the ocean, just due to thermal. Actually, it's warmer and water expands. When you include the ice loss, you get the dotted black line here, which is pretty darn close to the actual data here. This next one is the rate of sea level rise in millimeters per year. And the colored lines, again, are data. You can see they don't all agree with each other very well. But you can see the two black lines are doing a pretty good job. There's something new in the recent data, by the way. This red piece up here is altimeter data, and this is also altimeter data. And these down here are shorter time frames. This is going from 1960 to 2010, and this is 1990 to 2010. And you can see how well in the recent years these models are doing, but they're not doing too badly up here either. So in this long period, they account for 60%. The models are accounting for 60% of the rise, but 90% of it in more recent years. And the ice sheet contributions have the potential of increasing a lot. This will come up again, but just to throw out a number, if the Greenland ice sheet were all to disappear and flow into the ocean would rise 7 meters. Serious effect.
Where do they measure that?
They estimated it based on knowing how thick the ice is and calculating the volume of it and what would happen if it all disappeared.
Antarctica's like
Well, wherever the sea level.
Antarctica is way more.
53,
But the thing is, Antarctica isn't as much of a threat because it's not melting, whereas Greenland is. So that's the reason Greenland is sort of held up there. Yeah. So okay, this is again more detailed modeling. This is up here. We have the Arctic ice extent as a function of the time of the year, and this is between 1980 and essentially 2000. And this is in square kilometers times 10 to the 6th. And this is so you can see in the Arctic winter, the ice extent is large, and in the Arctic summer in September it's down. There's two sets of data, measurement data that's shown here. There's the 2007 data, CHIMP 3, and then there's the 2013 data, CHIMP 5. If the CHIMP 3 data, the actual mean is this thin blue line here. The red line is the CHIMP 5 mean. The spread is by the color. The blue spread is the spread of the CHIMP 3 models, and the red spread is the standard deviation associated with the CHIMP 5 models. You can see that both models are doing a decent job, but the actual red is doing better. Now, if you go down to the Antarctic, the spread is way bigger, you'll notice that the blue line, now you can see things are reversed. In the month of September, that's the winter. The blue line is showing overestimated the sea ice extent. And the red line is right on there. It's right on there. So, amazing. And this is showing even another level of detail beyond this. This is actually showing the distribution. So this is the Arctic in March, in the winter, and this is the Antarctic in March, the summer, and this is the Arctic in the winter. Now, in this case, these colors mean different things. The red is the actual extent of the ice, and it's a mean because it's an average, but it's the mean. And the colors are indicating the number of models. So you can see there's as many as 42 models in play here. And the ones that would have all gray, like up here, it says all 42 models were correctly predicting this. So it's doing a pretty darn good job. The one that isn't doing as well is the Antarctic summer. And it's, you're down into the green areas here, in the yellows in a few cases. So you're dealing with only about maybe 15, 12 to 16 of the models are doing this correctly. But the other 3 seasons are pretty amazing. So again, I think this is another effect that's modeled here, but this is measured and modeled. We're looking here at the frequency of the coldest nights and the coldest days. And this is the bottom 10% of temperatures. How often do we get days that are that cold? And this is a frequency percent. And this is time. You can see the data is showing a significant drop in the number of coldest nights and coldest days. And on the flip side, the number of warmest days is going way up, both night and day. And again, I'm showing the model results. The red model results are following the data remarkably well.
And is the black actually measured?
Yes, the black is measured.
Yeah.
As most of these graphs, the black is measured. That previous one was the one that wasn't. The red happened to be the measured, and the black was. But in this case, the black is the measured data. Several data sets. That's why there's so pretty interesting. So I mentioned that there were some new effects that are being included in the latest generation, and one is the carbon cycle. And so this is plotting the atmospheric ocean flux in petagrams per year, petagrams C per year, and it's and everything above 0 means that it's sinking, it's absorbing CO2, and the data is this black line. And if you want to know where that data came from, read this paper here. But that is the data. This is the actual calculation from the CHIP5 model, and the color here is the confidence level. So as you get up to 90% confidence, you're in this band here. And this is the total realm of all the models. And then this is the same thing for the sink source for the Earth itself, the land. And as you can see, nothing is happening here. There's very little change in the storage of CO2 on the land. Much more, but you're seeing a significant pickup in CO2 being stored in the ocean. But again, modeled results.
So the land CO2 is all vegetation, basically? Is that?
Yeah, and it can be stored other ways too.
Yeah, in mineral.
That's a long term. The vegetation is a quick.
Yeah, that's better, yeah.
And the ocean storage is dissolved in the water, is that all it is?
Yeah, that's it. Yeah,
So
it's
now,
dissolved
if you
in water.
dissolve CO2 in the water, is that good or bad?
Ocean acidifies.
Depends how much.
Depends if you want Perrier or.
We're going to talk about ocean acidification a little later, but yeah, it's not necessarily good, but it helps take CO2 out of the atmosphere, which is good. Okay, so this is kind of a summary of a lot of the stuff that went into those models, and this is called radiative forcing, and it's the change from 1750 to 2011, and the units are watts per meter squared. And here we have these are divided up in categories. This is called a well-mixed greenhouse gases: CO2, methane, nitrous oxide, and you can see the bulk of this is CO2. The error bars are the uncertainty of the data. And the error bars are relatively small up here. Then if we come down, okay, and I'm going to come back to the light green is ozone. I'll come back to that in a second. This is the short-lived gases here, and you can see that there is some of this is cooling. And then this is where the real complexity in these models are. In addition to the clouds, is the aerosols. So these are the various aerosols and precursors that are embedded in the model. You have ammonia, sulfur dioxide, black carbon, organic carbon, mineral dust, aerosol, cloud effects, and aircraft, contrails, very small. But, and you can look at this, you can see most of this is on the cooling side, but there is some on the warming side, and that's essentially black carbon, also related to biomass burning and fossil and biofuel effects. It can actually cause a radiative increase in the radiative positive forcing, which means higher temperatures, and negative forcing, meaning cooler temperatures. Land use has a cooling effect because we've taken trees away and forests away, so the surface of the Earth is reflecting more. So the albedo is going up, so we have less solar radiation impinging, so it's a cooling effect. And then the solar irradiance is shown as a small increase and this is an average over this entire period. And if you go down to this, you can see the changes. This is the total anthropogenic, and this is all man-related, anthropogenic. The total from 1750 to 1950, and this is to 1980, and this is to 2011. So,
Very bottom here, you have 1750 watts per meter squared.
rating relative to 1750 in watts per meter squared.
Oh,
17.
AD.
Yeah.
In watts per meter squared.
Yeah. This is not my error. This is a part of this chart that was I clipped. But and you can see that these IPCC reports give this in confidence levels, and so they have this in high confidence, this in high confidence, and this in medium confidence. And you can, if you want to, you can get a more precise definition of these from in the reports. They give all of that. So this is the kind of the input to these models. And well, yeah, I said I was going to talk about ozone a little bit. So ozone is a complicated thing because in the stratosphere, it's a cooling effect because it's absorbing ultraviolet radiation, and that's where it is here. But ozone is also a product of pollution, and so you get chemical effects associated with the sun causing chemistry in the atmosphere with various compounds like methane and also some of the aerosols, and so you get ozone created in this process. Now this is in the lower atmosphere, in the troposphere, but you can see that the net effect of ozone is mostly warming because it's all this indirect stuff that's occurring because of sunlight creating the ozone in the troposphere, pollution. So ozone is a complicated story. Most of the error bars here, you see the error bar here, it's pretty large. Most of it is down here in the aerosols because this is where the biggest uncertainties are. And it's where most of the work is going on in trying to improve the modeling here. And I was talking about the aerosols, so I'm going to spend a second or two talking about the aerosols. Aerosols are pollution, man-made pollution, and it's all those things that I talked about. But there's these latest models include it in a couple of ways. The direct effect of the aerosol generally is a reflection of the sunlight, but there's indirect effects because the aerosol can actually be a source of cloud nucleation, which can also cause increased cooling. And it can also add to the reflectance of clouds, and this is called the aerosol cloud effect. And it makes more of the sunlight reflected. So this is what they call an indirect or a feedback effect associated with the aerosols. And
so China shouldn't clean up their air?
Yeah, well, you see, we're going to get to that. That's a very good point because that's where I'm going with this now. this is all, these are the aerosols as a function of time. This is all the aerosols, and you're looking at 1930 to 1850, 1980 to 1850, and 2000, versus 2000 versus 1850. And for all the aerosols, you can see the net effect is cooling, and So that is, we would have warmer temperatures if it wasn't for the air pollution. Is the bottom line. But they peeled this off. These next rows have peeled off some of the stuff. So this is just the carbon part. The carbon part is warming. This is the ozone part, and as you can see, it's cooling in Antarctica ozone hole, but it's warming everywhere else. And this is all the models, but this includes these radiative effects. This is called the effective forcing, radiative forcing, and it includes the effect associated with more clouds being formed and sunlight reflecting off of clouds. And it takes the number from minus 26 all the way to minus 1.17 watts per meter squared. So these are some of the feedback effects that the models include in this generation of models. But when John talks, you're going to see a very different story here when we look out to the future and we clean up the pollution. And this changes big time. And that's the reason I'm going into the detail here, because it's a big effect, as we'll see shortly. Okay, so this is getting towards the end of this chart. But this is now a chart also from the reports that shows both the anthropogenic and the natural radiative forcing, both of them, on the same plot. And I'll work you through this. And this is, again, effective radiative forcing in watts per meter squared as a function of the 1750 to 2000. So the top is the solar effect. And so yours is this 11-year solar cycle that we were talking about, through those bumps. The next is black carbon on snow in airplane contrails. And there's just a thin black line there that disappears as you get down here. Then there's a stratospheric water effect, and it's a relatively thin line. Then you get tropospheric ozone, which is up here. Again, these are all warming effects. You get into other well-mixed greenhouse gases. That's what WMGHG means. And you get this area here. And then the very lowest you get here. And okay, so that's all the warming side. On the cooling side, we have the aerosol radiative interaction, the ARI interaction here, which is how seeding clouds, aerosol cloud interactions, increasing cloud reflectance, land use changes, Earth albedo changing, increasing. And now we also get into the stratospheric ozone, which is the effect of ozone taking the UV out of the sunlight. And lastly, the volcanic, which is again a natural radiative forcing. The volcanic is this light green. And then the sum, the total anthropogenic sum, is the red here. And the total, including the natural effects, is the black line. And it pretty much follows the red line, except for these big dips when volcanic effects occur. So this is so anyway, that kind of gives you kind of the bottom line picture of what's going on. And this is the last chart I'm going to show in this. Well, I show one more summary chart, but this one is kind of one I wanted to end up on because there's a lot of stuff here, so I want to walk you through it slowly. But it shows a lot of what the models have been doing. There's a sea ice extent up here and down here. So this is the Antarctic sea ice extent, and this is the Arctic. And the way the black is the data, and the red is the total, the purple is the total spread of the models only for natural effects. And the red, the pink, includes the natural and the anthropogenic. And so that's one effect here. The other is the ocean heat content. And this grouping here is the North Pacific, the North Atlantic, and the South Pacific. And this grouping here is the South Atlantic, the Indian Ocean, and the Southern Ocean. And one thing you can see here immediately is that these effects are stronger. The ocean heating is stronger in the north than it is in the south here. And then if you look at the continent temperature, the land temperature, changes. You have North America up here, you have Europe up here, you have Asia up here. Look what happens when you look at Australia, much less rise, and much less rise, and Africa somewhere in between. This is South America, somewhere in between. Oh, it's low. South America and Australia look very similar. So you can get a feel for the total dimension of what this modeling does. And here's the summary. This is the overall summary of land surface temperature, land and ocean surface temperatures, and ocean heat content. So, my last picture slide. So this is a summary. I'm going to give a summary of what we just talked about, but this is also a summary up here. And what's plotted here is the pattern correlation between the data and the models. And this is shown for 3 generations of models, CHIM 2, 3, and 5. And so you will see the green is the average, and the green is, and this is relative to surface temperature, by the way, is 0.99. So the correlation between the actual model and modeled surface temperature is very good. You'll also notice that the blacks are the spread in the data, in the models, and the spread is getting better too. So the correlation is approaching unity, which means it's doing a very good job, and the spread between the individual models is smaller. Precipitation is not such a good story. It's obviously more complicated, but it has risen, particularly in this generation, and it continues a very slow rise. But what you notice in the CHIM 3 to 5 is the spread in the models is much less. So we're doing a better job with the precipitation as well. So from this and the previous slides, you can see that the models are doing, I think, an amazing job of modeling all matter of climate processes. The average surface temperatures on land and sea and the combined, but they're doing way more than just the average. They're looking at the actual patterns across the globe in both temperature and precipitation. They're looking at the changes in the coldest and the warmest days, and they've done a great job of modeling that, showing the ice sheet growth and glacier growth, as well as the details of the ice extent throughout the seasons. And we're looking at the sea level changes, sea temperature changes, and sea heat content, and doing a good job modeling those. And we're also including these very complex effects of radiative cloud effects and aerosol effects and their associated interactions. So with that, I'm going to take a breath and let John pick it up from here.
Mike, should we take
Yeah, there was a CHIM 4. And they, for some
Who
reason,
killed CHIM 4?
I mentioned CHIM 4 when I was describing some of the models, but there's okay. So we're going to take a little, I'm going to hand the baton.
Should we take a little break?
Yeah, maybe a short break, bathroom break.
Yeah.
Okay, why don't we take a 5-minute break?
Boy, John, you know how to do everything more than that.